So please, Professor Kitipornchai.
I think what he meant is that I'm the oldest person. But anyway, I'm happy to accept that honor. I don't think anyone is older than me, right? Okay. Today I'm talking about FRP, even though it's really not my area. I thought I should present some work of my colleagues in the University of Queensland. Now, FRP or fiber reinforced polymer are made using continuous fibers, which are embedded in polymer resin matrix. The types of fiber used in civil engineering are including aramid fiber, asphalt fiber, carbon fiber, and glass fiber. And FRP products typically come as FRP fabric, protrude plates, or protrude profile. When it comes to use the FRP, there are a lot of use in the strengthening and confinement application of concrete structures. There are a lot of advantages using FRP because one of the biggest advantages is the high strength to weight ratio as in the flexural application. This is very easy. It's also very easy to install due to its lightweight. FRP is also has a very high corrosion resistance and has the flexibility to follow shape of curved surface. For example, for wrapping around this bridge pier in such a marine environment, which will be a problem using steel. FRP has high corrosion resistance and can follow curved surface, and therefore is ideal for such an application. Now we look at the typical mechanical properties of FRP. This table shows the four mostly used FRP. CFRP typically has the higher tensile modulus and tensile strength. The glass FRP has the lower elastic modulus and tensile strength, but has higher strain capacity. Now when you look at the stress strain curve of FRP compared with that of steel and concrete, you can see that it's clear FRP has very high elastic modulus compared with concrete. In terms of attraction to the load for concrete, this is very easy because of the high stiffness of the FRP product. However, when we use FRP with steel, the advantage of high stiffness is no longer there because steel elastic modulus is quite comparable to FRP. So this means that we need to be more innovative when we use FRP with steel. But due to the high strength to weight ratio, pre-stressed CFRP has been used to strengthen, for example, this aging bridge in Switzerland to enhance its fatigue performance. In this example, CFRP has been used to repair a penstock in America, which has a significant thickness loss. And this is because it's very easy to install in a curved surface, and the cost of employing CFRP is much cheaper compared with other options. And indeed, you can install either on the inside or the outside. In this case, because of the significant losses in the thickness, the CFRP was installed on the inside, and you can see that it was very easy to install on the curved surface. Another example of using FRP is in the steel structures in this example to prevent the elephant foot buckling in the steel pipes using FRP jackets with fiber oriented predominantly in the circumferential direction. This will delay or eliminate the local buckling and therefore will enhance the ductility of the member. Now, in terms of strengthening of steel members using FRP, we can categorize them in terms of the performance of the bond layer. One is the one critical application where the performance of the strengthening depends on the interfacial shear stress transfer from the steel beam to the FRP plate through the adhesive layer. The second category is the contact critical application, as in the confinement application. In this case, the performance of the bond depends on the interfacial normal stress transfer. In this case, the adhesive has much less critical role. So our discussion will be restricted to the bond critical application. Now, for an adhesively bonded FRP to steel bonded joints, there are 3 materials and 2 interfaces involved. Possible failure modes could be material failure, such as the interlaminar failure, CFRP rupture, or delamination, and adhesive failure. The adhesive failure is referred to as the cohesion failure. Failure could also occur at the interface. If the adhesion failure occurs, it means that the adhesive property as well as the surface character is a problem. In other words, how well the surface has been prepared. On the other hand, cohesion failure depends on the adhesive properties. The adhesive strength from chemical and mechanical bonding, it can be shown that with proper surface preparation, such as removing the weak layer, roughening, cleaning the surface, this will improve the adhesive property quite significantly. Therefore, with proper surface preparation, this means that the FRP steel bonded joint, we can avoid adhesion failure altogether, and therefore we conclude that failure will be due to cohesion failure within the adhesive. We need to understand the effect of different adhesive mechanical properties on the bonded behavior of the FRP steel bonded joint. To do this, we use the test method called the single shear pull-out test, which is often used to study the bond behavior of FRP to concrete and FRP to steel bonded joint. With a strain distribution along the bonding length, the bond-slip relation can be obtained. Now, in this study, we use 4 different adhesives which are commercially available. The Sika 330, which are the recommendation from the industry to use for FRP steel bonded joints. You can see that the 2 adhesives have high elastic modulus and high tensile strength, but they are almost linear elastic and brittle compared with the 2 erudite adhesives, which are non-linear and ductile. You can see also that the load carrying capacity of the bonded joints made from linear adhesives with high elastic modulus and low strain capacity can be lower than the samples made from the non-linear adhesives with lower elastic modulus but higher tensile, higher strain capacity. So the bonded joint is much more ductile with non-linear adhesive when the non-linear adhesive is used. This observation indicates that the load carrying capacity of such bonded joint is not solely determined by the elastic modulus or the strength, which means that the industry recommendation is actually not quite correct. Now, for FRP to steel bonded joints with linear adhesives, the bond-slip relation or the interfacial shear stress-shear slip relation can be analyzed as a triangular curve, as you can see there. While the bonded joint with nonlinear adhesive, the bond slip curves can be simplified as a trapezoidal curve. It has been found that the load carrying capacity of such bonded joints can be calculated with the expression in which the fracture GF is the fracture energy calculated as the area under the bond slip curve. For FRP steel bonded joints, the fracture energy can be expressed as a function of the adhesive thickness and the strain energy. So it can be seen that for a given FRP property and geometry, the bonded joints with non-linear adhesive has greater fracture energy than the ones with linear adhesive. Now let us look at the behavior of strengthening steel beams. When we strengthen the steel beam, even for class 1 compact section, there are many possible failure modes when you put FRP plates. It could be failure due to debonding, which can be platelet end debonding, or intermediate debonding, or FRP rupture. Or it could fail by flange buckling or web buckling. This is because the addition of the FRP plate, we actually shift the shear center and the centroid of the section and put higher stress on the web and the flange, causing possible flange and web buckling. Now, fatigue strengthening. Fatigue strengthening is one of the most advantageous aspects of strengthening of steel structures using FRP, since no welding or bolting is required. Fatigue performance tends to be very good. It has been shown that by applying pre-stressing on the FRP plate, you can reduce the stress concentration at the crack tip of the steel plate, hence increasing the fatigue performance. We need to consider that when we apply the pre-stress to the FRP plate, we are actually introducing residual stresses in the adhesive, and that tends to weaken the adhesive itself. And therefore, the optimum solution is the amount of pre-stress applied on the FRP plate to reduce the stress intensity, and that doesn't weaken the adhesive too much. Now, this is a test done by my colleague, Dr. Dylan Fernando, which showed failure due to debonding followed by rupture. The application of the pre-stressed FRP plate has actually increased the fatigue strength quite significantly. Now, some studies also have shown that FRP can be used to strengthen this rectangular hollow section against web crippling. The studies show that the inclusion of FRP plate can change the failure mechanism of this type of cross-section and therefore increase the strength of the section quite significantly. The other study have tried to use FRP plate to strengthen the column against global buckling, but this has no real improvement because the FRP plate is not likely to change the stiffness of the column any significantly. As I said, another very interesting application of the FRP is the suppression of the local buckling in circular hollow sections, which can also be applied to silos. This shows that because of the confinement, the localized elephant foot buckling mode has changed to global buckling mode. Also, you can see that the load deformation curve shows that even though you don't get significant increase in the ultimate load, the post-ultimate behavior changed quite significantly. You have high increase in ductility compared with the bare steel, and so in the seismic region, this obviously is a very big advantage. So, in summary, I can say that external bonding of FRP reinforcement has been clearly established as a promising alternative to strengthening technique of steel structures. Now, before I conclude the topic on FRP, I would just like to say that this is a very topic that's very well researched, in the sense that nowadays FRP is being used not just with steel and concrete, with timber and with all kinds of combinations. So clearly, it's leading to a lot of innovative design and so on. Now, if you wouldn't mind, I just want to go back to my own topic, which, of course, as many of you know, I worked early days on stability, nonlinear analysis, transmission tiles, and smart structures and materials. And so, one of my favorite topic is transmission tiles. And this was because yesterday when I listened to David Nethercott, my very good friend, he always said, when you do research, his advice to the young people, he always said, look, so what? Why are you doing the research? What is it going to end up? What is it leading it to? So with that, I really want to share this with you. One of my favorite topics that I have done almost 30 years ago is numerical simulation of the ultimate behavior of transmission tile structures. and I'm sure that many of you have listened to me before. I have, this particular structure is one of the structures that I like very much because it's my, as I said, my research topic. We talk about bridges carrying traffic, but we need transmission towers to carry electricity. There's no other way of doing it but using transmission towers. But yet this tower structure is very little research done. And when I look back over the past 25 years since I've done this work, there has been very little work that anybody has done. And in fact, this kind of structure is usually not done by structural engineer. Usually handled by mechanical and electrical engineer. I do not know why. And failure is very common. I mean, I'm just showing you a few failures. That one in China. In fact, it occurs all the time. And it's just not been publicized because nobody got killed. So when that's the case, usually they just prepare and get on with life, I suppose. But I would say to you that even though I've done the work 25 years ago, current methods of analysis cannot accurately predict tower behavior. And as a result, you may not be aware of this. It has been necessary to carry full-scale testing, even today. In fact, transmission towers is the only type of structure in the world that still require regular full-scale testing. So there are literally thousands and thousands of full-scale experimental data. But yet, no correlations of test data can be made with analytical results. So I would say that this is one of the most difficult structure to analyze, and this is what I said 25 years ago. And the reason for this is because of the complexity associated with the angle members used in the tower. Angle members, even though look very simple, is very, very complicated. It's a symmetric section, open section, eccentrically connected at all joints. So an angle member's principal axis do not coincide with the axis of the frame. The degree of illustrate and the 3D joints is also not easily quantified. So just imagine you want to try to simulate the behavior right through to failure. It's not that easy. Basically, we have to incorporate geometric nonlinearity, material nonlinearity, joint flexibility, joint eccentricity, joint slippage, asymmetry in the angle section, and large displacement. I would challenge any of you, if you are aware of any other software or methods that can do this. We have developed a software called AK Tower, as I said, 25 years ago. And we are able to accurately simulating the ultimate behavior, not just the ultimate load, but exactly where the failure occurs. You can see this particular slide. This prediction was done before the full-scale testing was carried out, and the failure load was within a few percent of the failure load, and also where it occurs as well. So I would say that even though this technology was developed over 25 years ago, and we have published lots and lots of paper, and there's no reason why anyone else, a lot of PhDs, cannot even do something better than that. But I know for a fact that until today, this technology remains unchallenged. And so, at the moment, there are interests in China, which, because as you know, China has got a lot of towers with the Belt and Road and so on. There are literally thousands or hundreds of thousands of towers going to be built. And as I said, there is no technique that can predict or design the tower that I'm aware of. And I've given lots and lots of talk, and nobody ever able to tell me that there is such thing. And that's the reason why testing station is still flourishing everywhere. So basically, and we've done a lot of consulting job. In fact, we have basically simulate all the tower design in Australia, New Zealand, and some in UK and so on. And to the point where a lot of utilities now believe in us and don't do full-scale testing. Because the software can be used to verify tower design. And in fact, the full-scale test cannot capture the real behavior because the load cannot be free loading. The load is a follow load. So you can never test the tower in reality. But our method can replace full-scale testing. We can use to check, upgrade old towers, which is what we have done in some towers in the UK, because nowadays it's very difficult to build new transmission lines, because of the environmental issue. So they quite often want to upgrade the tower capacity. So our method can be used for that. And of course we have used the software to investigate tower failure, optimize tower design, and also come up with some innovative new design. But the most important thing is very cheap compared with full-scale testing. So with that, I want to finish it by just sidetrack, but a bit on the FRP on my own topic. So thank you very much.
Thank you very much.